Shall we begin?
Sure.
Okay. So welcome everyone to the Growthentic School of Thoughts. Today speaker is Dr. Rahul Gupta from HRI, and he will talk on algebraic K-theory of schemes. And I think the title of the talk is K-theory and G-theory of schemes. So please.
Sure. Thank you, Maina, and thank you very much for the invitation to give a talk here. So even if this is we are recording this video and everything, but still I would like to be a bit informal. So please do ask questions. I will try to answer them as much as possible. Otherwise, I will answer them next time. Okay. So let me start the talk with giving some references. So first thing which I like maybe especially young PhD or postdocs to read is this notes that development of algebraic K-theory before 1980 by Weber, Czech Weber. This just gives you a brief idea of history of algebraic K-theory and topological K-theory also. There's a session. So it's a good start why and how the things progressed in this area. And you have seen most of the progress in this series of lectures. Okay. So next reference is, as most of you know, this. So I will follow this higher algebraic K-theory book on paper. Algebraic K-theory by Cullen. And whenever this reference is there, then automatically Srinivas book comes. So that is yes, algebraic K-theory. The book of Srinivas. So I will follow basically these two books, and one good reference is always K-book of Weber to read more about K-theory, algebraic K-theory. Okay, so these are the references, and I would like to stop here and say to you guys that let me know if my handwriting is not readable or if my voice breaks. Okay, please do let me know. Cool. So there is this call with some recollection. From your basically previous talks in this series. So the first thing which you guys have learned is that given an exact category, how Cullen defined its K-theory. So Cullen K-theory of exact category was defined to be, so what we do is that we take exact category, do Cullen construction, take the classifying space, take the loop space in that, take the zero object, zero loop, and take the pi i's of this topological space. So these are the K-theory of exact categories, right? So this was done by Vivek, if I'm not wrong. Second thing which we kind of saw in the last lecture of Gircha was that if R is a ring, then you can define the K-theory of the ring R to be, what you do is that you take GL and R, GL infinity R, do a plus construction of pulling, and you tensor with the Grothendieck group, basically, and take the pi's of this, right? So this was the definition of higher, like K groups of a ring. And one of the things which I guess you guys have seen this statement, at least in the proof, that these groups are actually isomorphic to the, let me put a Kulin here just to, let me put just Q here, just to say the Kulin K theory of exact category. So what you have seen in the last lecture is the statement was stated, is a Kulin K theory of exact category coming from the projective modules, projective modules, where P of R is the exact category, of Northallian, category of finitely generated projective R modules. Okay, so this is the exact category which is associated with any ring, the exact category of projective R modules, and we take the K theory of that in the sense of do the plus construction. So that means let us go a bit slowly and try to rewrite it. What does it mean by the first step? So what we are doing is that we take this category, do a Coulomb construction, take the classifying space, take the loop space, it has a 0 element, 0 loop, and it take pi i's of this. Right? This is the definition of K theory of a ring. And you guys have seen this G theory of ring also, which was defined in a similar way. So I will write in this form just to emphasize that it is this kind of construction is there. So this is, again, you take the some abelian category, some exact category, and do the Coulomb construction, classifying space and loop space, where this MR is the category of finitely generated R models, right? So these definitions you guys have seen, I believe. Yeah. Okay. So I would love if one person at least can respond. It would be nice because I can't see anyone's face also. Yeah. Okay. So one more thing which you guys must be knowing is given any scheme. So I'm okay. So I did not say this. I'm going to assume algebraic geometry as a prerequisite for this talk. And if you have not seen algebraic geometry, the results which I'm going to talk about today, I will recommend them, like these are a good starting point also to go back to algebraic geometry and see the things which I'm going to do. Okay. So if you have not seen algebraic geometry, you're learning algebraic geometry, don't get disappointed. Do listen to the talk, do go through the terms, and then you will learn and come back to the talk. Okay, so that is the general idea. So what happens for any scheme? Let X be a scheme, and so then Grothendieck defined a group associated with X, which we call as Grothendieck group, K naught of X, which was, so it is defined for any exact category. Let me just focus on the scheme for it. So you take the free abelian group generated on where E is a vector bundle, is a locally free sheaf. So locally free OX module. Yeah. And then you go modulo the relations coming from the short exact sequences. 1, 2, 3 is exact. Then I declare E2, a class of E2. I will declare class of E2 to be same thing as class of E1 plus class of E3. Yeah. So most of you might have seen this definition earlier. So given any scheme, we can always associate this Grothendieck group with X. Okay. And the point is, like, the starting point of all this K3 was these Grothendieck groups. So what I'm trying to say is that even if you, so first of all, you know, okay, yeah. So we have seen that there are K theories of a ring, general ring, but we also have this K naught of R, K naught G of R, X, basically, for schemes also. So it was very much the need of the hour to define the K theories of a scheme. Okay? Is it okay? Or is it motivation enough?
Yes.
Yeah. So now let us define. So now let us go to the lecture. So let us fix some notations first. I don't want to work in a very general setting. So by a scheme, can you see my slides?
Yes.
By a scheme, X, we mean, today we mean Noetherian quasi-separated. Sorry, separated. Noetherian separated scheme X. I'm going to assume one more thing, with an ampersand bundle. Okay. So for example, one can work with, for example, we can take quasi-projective schemes. Quasi-projective schemes. All of it. So usually in algebra geometry, we work with this class, quasi-projective schemes who are field, or if you want to work with a huge class of schemes, this is also not a bad category, like Noetherian separated schemes with an ampersand bundle. So I'm going to always assume X to be of this type, even if the definition and many properties will make sense for any scheme. But let us not go there today. Okay, good. So let us make a definition. So for a scheme X, and so okay, and I equal to 0. We define Ki of X to be, any guesses what it should be? Can someone say what about should I write? Which exact category should I take? This has to be clean K theory of which exact category? Anyone? So what we did? So okay, yeah. So what we did, recall that what we did for rings. Let us go back. So what we did for ring, we took this category of projective modules, right? We took this category here, which are projective modules over the ring R, find J projective modules. So what is the correct notion of projective modules when we go to the schemes? Anyone?
Are they coherent?
They are coherent, but projectiveness is an extra condition, right?
Yeah.
So what's the correct notion of projective in terms of the schemes?
Vector bundles.
Vector bundles. So you might remember from your computer algebra course that projective module is finitely generated module is projective if and only if it's locally free. Right? So the projectiveness is kind of locally freeness. And for schemes, that concept is what we call as vector bundles. Okay. So I hope that this kind of justifies what I should write here. I should write as an exact category. I will write px only. Sorry. I want to put x here. Px where px is the exact category of. It's a good exercise to prove that it's the exact category also actually. Exact category of I've let in terms of sheaves locally free OX modules, and I have to put finiteness condition of finite rank. Right? So point of the K theory in some sense is why we define something like this, or for range, for X, for anything. So the general idea of in algebraic geometry is a scheme is basically determined by vector bundles over that, or locally free sheaves over that. So if we can associate some groups with that and study these groups, we must be able to identify our X, which means that we should be able to differentiate between two X if their K theories are different. That is the expectation. And that's why we define these groups. So this category is very important. We will see in a moment that there are other categories associated with X also, but this is the most crucial category. And that's why you many times in algebraic geometry, you hear the people studying vector bundles in differential geometry also. And it brings people study projective modules. There are very, very important subcategories of all modules, all coherent sheets. Okay? Is it okay? That is the definition. So let us write the definition completely, okay? There is no need to hurry up. So what is this? This Ki of X is, so I will start with again, P of X, exact category, do a Coulomb construction, do a classifying space, loops. There is a point here, which I'm going to avoid from here on, and take the fundamental groups of that. Okay? So these are higher fundamental groups of a topological space, which is a loop space actually. So these all KIs are actually available. Okay? Good. So, okay, what should be our G theory then? We define this is a definition, and let us write G theory. So it should be just, let me write in terms of exact categories, not write this. So this is Coulomb K theory of which exact category now? So GI of R was, let us go back. So GI of R was, here we took basically category of all finitely generated modules, right? For MX, basically MR. So what we'll do for R modules is just in algebraic geometry, they will be OX modules, right? So they are sheaves with a module structure, OX module structure. Finitely generated translate to coherent. No, sorry. OX modules will translate to quasi-coherent, and finitely generated means coherent. So let me write this. This is just K theory of M of X, where M of X is a category of. So this forms an abelian category actually. So this is very good exercise. If you have not seen the definitions of these categories or Ki and Gi, you should prove that these are abelian categories and exact categories respectively. The abelian category of coherent. Yeah? Is definition clear? Okay. Okay, so let us just do a sanity check that we are not doing something very weird. So if I take K theory, so as we described earlier, if I take the K theory of spec R, there is a scheme associated with a ring, is actually nothing but the K theory of R, right? So this is defined, this side is defined by projective modules. Projective modules, this is I'm saying they are locally free sheaves over R of finite rank. And what we said earlier, what is the motivation of the left-hand side was that it should be same thing as right-hand side. So projective modules are same thing as, finite projective modules are same thing as locally free sheaves on a spec R of finite rank. Yeah? Is it okay? Everyone with me?
Yes.
Good. So let us go to, so this is the same thing happens for G also, right? So we get back to our definition of our last lecture. Basically, we get KIs and GIs. So it's an extension of the theory from K theory of G theory of rings when we go to scales. This is our first sanity check. The second sanity check said, if I define K naught of any X, is it same thing as Grothendieck K naught? Right? Because I have two K naughts, and if they are different, I should not use K naught. I should use something else, some other notation. Okay, so this G is just a, yeah, just a differentiate that this is the Grothendieck K naught of X. Okay, so it's a theorem of pulling that actually they are same. Yeah, they are actually isomorphic. See, this side is defined just by generator relations. So sorry, right hand side, actually this side is actually defined by generator relations. Very nice. This side is defined as pi naught of some loop space or some topological space. You see that both the definitions are very different in flavor, and but requires a proof that these two things are same. You know, for rings, for exact categories also can make the same kind of definition. They are actually same for any exact categories. So we are saying for X it is same, and let us try to see the kind of a map, at least like one side of map we should give, and it's an isomorphism will be a theorem. Is it okay? So what I want to do is like to give a map just to get a flavor. Okay, so let us write. So what is this thing? This is pi naught of Px Q construction and classifying space and omega. Yeah. Okay, so if I take a, so here it is generated by a vector bundle. So let me take E, be a vector bundle over X or locally free sheaf over X. Now, this is an element of this category. So E is an, so let us write. So E is a element of, is an object of, is an object of Px, which is same thing as, this class is same thing as objects of QPX, right? Let me write one more thing here. So around 0. This is pi 1, right? So this is pi 1 of BQPX along this 0. Okay. So now given any E in projective module, which are generators of this this side, I get an object of QPX. So which is same thing as this gives, this implies that. Okay, so this is the object of QPX. Fine, so what? But I want a loop along 0, right? So this, an element of this fundamental group is a loop around 0. So I have to give a loop around 0. So what we will do is that we give a map from 0 to this E basically. So E is an object of, E is a point in this B classifying aspect of QPX. And if you give a map, if I give two maps from E to 0 to E, I can take a loop. Everyone with me? People understand what I'm trying to do? Should I repeat?
Yeah, one.
Yeah. So what we're trying to do is that we're trying to give a, given any element, a vector bundle over X, I want to say where it maps to under this map. Say, let us call this map to be rho X. Yeah. So what are the elements of rho X? They are loops along 0. Right? This is a fundamental group. So there's a point, 0 point, and I'm giving a loop around 0. Okay. So how do I give a loop around 0? I will say that I have 2 points, E and 0, and I will give a path between them. and paths in this BQPX are given by basically morphisms in QPX. Yeah, in this category, if I give you a morphism, that is a path. And let me write this down, and then you'll see. Yeah, so these are the, recall that QPX, the Q construction was, objects were same thing as the exact category, and the maps were such epimorphisms and monomorphisms, right? So I get two maps from 0 to E. So this is gamma naught, this is gamma 1. The loop I'm going to consider along E, the class of E, I will map to gamma naught composed with gamma 1 inverse. Okay, this is a path, and I can take the inverse of the path. And this is a path, this is a map from, say, S1 to BQ. Okay, so if this is the first time you are seeing this construction, I would request that you can go to the definition of this topological space and see this, what I'm trying to say here. It will be a nice exercise. Okay. So again, this lecture is not going to be self-contained at all. So I want you guys to go back and read the definitions of this classifying space and Q construction and everything. Okay, so there's a well-defined map, there is a nice map, which we can explicitly write, and it's proven that this prove that is actually nice. So what we're saying is that the K naught of X is actually nothing but the Grothendieck. So we are in the correct on the correct line, basically. Okay. Is it okay? Yeah, so what I'm trying to say is that we define some Kulinke theory, some new theory of a scheme. For rings, it agrees with the last lecture. And for K naught, also it agrees with the well-known Grothendieck effects. So that's what we have said till now. Not proved completely, but that's what we said. Okay. So let me move to the next section, which is functoriality of these maps, these groups basically. Okay. So we have given some groups associated to a scheme, and we want to know what happens when we take a morphism of a scheme. So what happens to these groups, right? So let me write two kind of statements, and we will try to justify these statements in next half an hour or something. So we want to say that K of X are comolarity theories. The idea is coming from that this should be generalized comolarity theory, while GI of X are comolarity theories. Okay. Yeah. So let us say, in what sense we can make sense of it. This is something which is which are not a statement; they are just ideas. So this is just an idea, very broad idea that K theory should be comolarity theory, and G theory should be a comolarity theory. So which means that comolarity theories are those assignments which have pull back along all morphisms. Homologies are so that they have push forwards, right? At least that much we know. Okay, so let us start with at least with the pullback. Pullback in K theory. Okay, so what do you want to say here? Let f from X to Y be a morphism of schemes. Yeah. Then, okay, so these are the claims And yeah, then okay, let me write with we want what we want and then try to show why it is true. We want pullback of, for each I there is a pullback. We are saying for any morphism there is a pullback. So what's the recipe of constructing a pullback basically in this setting? That we have to go through. First, what's the recipe and how that recipe holds for any such a morphism. So is it okay if I go backwards instead of writing like, let me go step by step backwards, okay? So enough to,
Excuse me, I have a question.
yeah.
I don't understand why having this contravariant nature of Ki somehow relates to Ki being a cohomology theory.
No, this is a first step. So you want to justify as far as possible. So it's not a correct statement, it's just an idea. You want to justify like whatever you have basically in cohomology theory. So we will see, most likely we will see in the series of this two talks, there are many things which are satisfied by cohomology theory and they are actually satisfied.
Okay, so this is just one aspect.
Yeah, this one just aspect. This is the one starting point. It's the first thing which you want.
Okay.
Right? Cohomology means pullback. So a good way of remembering also, we should have pullbacks on K theory. Okay. Good. So enough to show that F induces hello. Can you hear me?
Yes, we can.
Yeah, okay. I just got a notification working offline. I don't know. Enough to show that F induces an exact functor which we also denote by pullback from P of Y to P of X. So how many of you agree with me that it is enough to show this statement? So have you seen this kind of statements in your talks or K theory of exact categories? Yeah. Hello. So what happens in exact categories? If you have a exact functor between exact categories, then there is an induced map on K theories. Okay. Yeah. So I'm not sure how many of you have seen because I did not find the notes on exact categories, but still I'm trying to, yeah, I will assume that. So this is actually enough to show that if there's a functor, if F induces a functor, if induces a functor between these two categories, whose K theory I was taking to be Ki of Y and Ki of X respectively. If it is an exact functor between these two categories, then if I take the K theory, it induces a functor. It is a map. Okay? Is it okay? Someone please?
Yes, it's fine.
Okay. So now, how many of you agree with me that there's an induced functor? Is anyone not familiar with such a functor? That this pullback is a functor from Py to Px. Anyone who has read algebraic geometry and not familiar with this statement? That would be nice to talk to that person.
This is,
okay,
you're talking about the inverse image.
So it's so good. So let us see. So it's not an inverse image, it's a modules, right? So I have to go back to modules. So let me write like this. So this is contained inside M of Y. And first thing I have to do is that I have to go back to M of X. So what we do, we have a, say, F, which is a OY module. What we do is that we take the inverse image, tensor with inverse image of OY, end, right? So then it's a OX module now. So locally, what we're doing is that, let me write local picture. Locally, if F is a map from, say, spec R, so this is my X then, yeah, this is my X then, and to spec R, so this. Then given any M in, say, MY, which is just modules over S, we define pullback of M to be M tensor with R over S. Yeah, it's a tensor. It's a pull. You take the inverse image, but you have to make it module. So you have to tensor it. Is it okay?
Yes.
Yeah. So these are the kind of identification which I'm obviously using. This is the kind of identification which I'm obviously using. And one person who has not seen the algebraic geometry or coming from starting algebraic geometry should see these kind of statements. This equality which I'm saying. Okay. So the point is now, if I take projective module, locally free module, locally free OM module, if I tensor like this, if I take this functor pull back, it is actually still projective, right? This thing is still locally free. So if F is locally free, then this pullback, this let me out, it's just a pullback of F is still locally free. Then because free thing will go to the free thing. And all these operations are defined locally and gluing them. Okay, so this says that, so what we have described, as we discussed, I'm not going to write everything discussed, we get a functor from this py to px. Then let me leave this exercise that this functor is exact. And it just follows that if I have a solid sequence of projective modules and a tensor with any algebra, so if I have solid sequence of S modules and tensor with R, it will still remain projective. Okay, and you have to see that this is the condition, like this exactness condition you can check locally, and locally it follows what the statement I just made. Is it okay? So in particular, so let me write, yeah, this is exercise. And I said I will assume a lot of algebra, geometry, computer algebra, unfortunately. So in particular, we get a pullback morph KIY to KI of X. That's good. Okay, everyone with me? Partially with me? So this at least says that, okay, I have pullbacks on K theory. On K groups, I do have pullback. So one can ask me what happens. Question, what happens? What happens when I take G theory? What happens to the pullback? G theory. Yeah, in this context, what happens when I take G theory? If I replace K theory with G theory, what happens? Any guesses? So what we have? So we had, again, let's recall, we had some functor X to Y amorphism, given amorphism. We have a functor. We just discussed this functor. We have this pullback functor from My to M of X. Yeah, so we do have this functor. Then why we do not get a pullback map on G theory? Yeah, but in general, this functor is not exact. See, all this Kulin construction was using this exact sequence is very heavy, right? So until unless your exactness is preserved by functor, some functor between exact categories, you can't expect the Kulin construction to go through. In particular, you won't get anything between K groups. Yeah? Okay? Note that F is exact when F is flat. Yeah? So our definition of flat morphism you can take it to be such that this functor is actually exact. It takes extraordinary sequences to extraordinary sequences of all finitely right OS models or coherent things. Is it okay? So in particular, we get pullback map along on G theory, pullback map on G groups, but along flat morphisms. So in general, we don't know. Okay. So I am 40 minutes into my talk. Okay.
In particular, in the case of Ital morphisms, thing.
Yeah, exactly. Ital morphism between schemes, we have pullback on G maps.
Okay, exact pullback.
Yeah. So yes, point is like exactness will come from when you talk about categories, right? These two categories, then we have pullback of exact. If you talk about G groups, these are just groups. So it's a group homomorphism. This pullback is a group homomorphism. Actually, it's a very interesting thing that why this pullback will be a group homomorphism also. But let's not go there today. Okay.
Yeah.
Good. So let me say it here. Let me make a side remark. So proposition. Okay. What is this? So this I'm not going to, if time permits, I will come back to this proposition, which I wanted to present, but yeah, unfortunately we don't have time. So let me write it and then we'll justify that F from X to Y be a morphism that has finite Tor dimension. Then there exists a pullback. From GIs Y to GIFX. Yeah. So what we are saying here, we are saying that we just don't need Italness. It's a sufficient condition, but it's not necessary. What we can do, we can relax this condition. So Ital is Tor dimension 0, and we can demand that if the morphism has finite Tor dimension, still we can pull back. Okay. So this follows. So I will just write a proof. So if people have seen the definition and everything, the proof comes from resolution theorem. Yeah. Theorem of Kulin. Let me just write in exact categories. So if time comes, I will describe this. But it's a very good use of this resolution theorem and how we basically work. So let me just discuss a bit maybe, and then I will move on. So what is happening? The point is like, okay, so my morphism is not flat, right? So this F is not flat. So F is not flat, but so note that F is not flat, This may not be flat. May not be flat. May not be flat. And hence pull back. If I pull back from all of m of x to m of y, yeah, sorry, y to x, may not be exact. Then how this finite thought dimension helps us, right? How the resolution will help us. So what will happen is that what we can do is that let me take this category. Let me use the correct notation. 1 second. Yeah. Let's take this subcategory of sheets in my such that if I take the such that tori of oy ox m is 0. Yeah. So which means the tau dimension of these modules, these oy modules, is actually 1 or 0. Yeah. Yeah. So they are basically on these things. Tensing with ox is actually flat. Then if I take this pullback map from py of f to m of x, is actually exact. Is an exact functor. And you can prove that the left hand side is also this category. This category is also actually an exact category. So I can take the K theory of both. And what resolution theorem tells me that K theory of one has to show, one can show, this is a big can, and can show that Ki's of P y comma f are same thing as Ki's of y by resolution theorem. And this is an exercise. We can go through the proof of in Colin's paper or anything. So there is a trick. So what you do is that whenever you want to define a functor between these two K theories, suppose there are K theories of two schemes right now, or to any categories, and your initial functor between the exact categories was not exact. You take the subcategories where the functor is exact and hope that by some magic it will become the K theories of these two things will be isomorphic. That may require some extra condition, which is here in this case is this finite thought dimension. Okay, is it okay? So this condition is very strong here. This is where we use this resolution theorem. Okay.
Yeah.
Good. So at least you get the flavor that what we do in this when we want to define the pullback in G theory. But I told you guys that motivation came from the fact that we should expect G theory to be a homology theory, which means that we should expect the push forwards to be there. So what is a good notion of push forward? So in K theory, there is no push forward, so we do not talk about that. In J theory, are there? So that f be from x to y. And we put this condition, we work with the proper morphisms only. Yeah. So we expect the push forward to exist between proper morphisms only. Okay. Then, so I want to like push forward. Huh? So then want, let me write want to define the g of x to j of y. We want such a thing. And recall that this was just Coulomb K theory of exact category of m of x, and this was just m of y. Yeah. So enough to show, again, the similar method, enough to show that pullback push forward is actually exact. Yeah, it's enough to show, right? This thing, if these are exact, then we will get the these are exact categories. We are saying that there's an exact function between them. We induce the take the clinical theories of these two exact categories. We get a map, push forward map. But unfortunately, this is so okay. So first of all, note that since f is proper, push forward of a coherent module is coherent OI module if M is coherent OS module. Yeah, so you need some kind of finiteness condition to assume that finitely generated modules are going to finitely generated modules. Yeah. Do everyone know how to take this push forward in for shapes for OS modules?
Yeah.
Yeah. So let me not go there. But you need this condition of properness to say that push forward of a coherent shape is a coherent shape. Coherent OS module is a OI module is a coherent OS module. Okay. Good. So at least we got the coherent, but we know that this is only left exact. Yeah. So whatever statement I was making here, this enough to show, yeah, enough to show this exact is actually not true. This statement is not true. So what we should do now? But the question was what we should do, and maybe we can say that okay, leave it. We don't have push forward on the G theory. But obviously, mathematicians do not stop. So we do the same trick which we played for the pullback in the previous section. What we do is that we take a subcategory where it is exact. So the notation is for that is like let fxf.
So to start with, F wasn't proper morphism, right? Or
So it was. So
okay.
we start with a proper morphism. When we're taking push forward, we're taking proper.
Okay.
All this. Yeah?
Thank you.
Okay, but the point is it's not exact here. So we have to take subcategory such that f is f lower star is exact on this thing, which is to say that higher derived functors of this f is actually 0 on this end. Yeah. So like we put the tor in the previous case, that tor 1 after tor it should be 0. Tensor should be exact on this subcategory. Here also we are pushing this Ri f star should be 0, so that f star is exact on this category. Then f star from f x comma f to y is the exact functor. Exact functor between exact categories. Both are exact categories. Yeah, so it's easy to see that this is the exact subcategory of my. Okay, so this condition is actually closed under. This thing is actually closed under extensions. Functor. So enough to show now. Enough to show that the induced map from K theories of this exact category to the exact category where it is basically there. M of x is actually an isomorph. Yeah, it's enough to show that then, because this is exactly the K theory of x, and then you will get the K theory of x to K theory of y will get a map. Okay. But this follows from. So we'll just write one line and leave it to the exercise, or come back to this afterwards. But this follows from resolution theory. Okay. Is it okay? Do people really want to see this resolution theorem and how these things follow? Or should we continue?
We can continue.
Okay. So, yeah, if you have seen this resolution theorem, it's good. You should try to verify the statements which I'm making. Otherwise, yeah, we can discuss afterwards. Okay, just give me a second. Yeah, okay, so we have some push forward and pull back maps, and now we want to write the proposition how these things behave with each other. Okay. So very first thing is that, so let me write it a bit vaguely. I don't want to be very specific. So if whenever there's a push forward makes sense on G theory, this composition push forward should be is actually same thing as composition of push forwards. Similarly, pullback also the same thing holds. Whenever there's a pullback is defined, you have to make this statement very precise, which I'm writing here, but I believe all of you can do that. If F and G have the properties that push forward or pullbacks are defined, then F and G will also have those kind of properties. All three of them have this property, then these things will be true. So this becomes functors basically then. Okay, so then Ki become, these Gi become factor on these subcategories, which we took to define where this pullback and push forward was defined. Okay. Third thing is this projection formula. How many of you have seen some kind of projection formula? Is any PhD students who is not working in K theory has seen this kind of projection formula? Okay, so what does it say? It says that how the pullback and push forward behave with each other. So let me just write it down and then we'll make it precise. So the idea is always you guys should be able to think what when someone is saying projection formula, what it is, and then make the things precise. Like everyone can do that. It's not a hard thing. So what is happening? So projection formula is something like this. So if you take push forward of x dot, okay, so this for this I need some more thing. Okay, so let me, yeah, there's one more thing which I have to mention, but let me mention after this. So projection formula says that if there's a product structure and I take the pullback and product with something on the top and then push it forward, then it should be just pushing forward things from the top and product with the y. Same thing in the second quadrant also. Yeah. So let me write where what we are taking where. So x should be in k naught of x and y. Okay. Yeah. Y is in gi of y. Yeah. So f given f from x to y. I'm taking something from the top, k naught of x, and something from the bottom, but that is from G theory. Similarly, x prime should be again k naught, but now from y, and y prime should be in gi of x. Yeah. Given this, such that, so I need to make sense of the pullback. So I'm taking the pullback on G theory, right? Here, I'm taking the pullback on G theory. I need to assume certain thing on this F. And then I'm taking the push forward also here on G theory. Such that F is proper, and of finite dimension. Finite dot dimension we have these equalities. Is it okay? What I want to say here? So let us read the now in linear way. So what we are saying is that given a morphism F which is proper and finite odd dimension, if I take x from k naught and y from gi of y, I can always pull back this y now to x, gi of x, and then I will just prove in a minute that k naught x on gi's. So then I have this product structure. I take the product. This is happening in. So this thing is happening in. This thing is happening in gi of this product structure gi of x, and then push it forward to gi of y. Same thing if I push forward my k naught class and then take the product of y in gi. And same thing happens when I do the other way around. Is it okay? So this is how you should think in any cohomology when there's a pullback and push forward between two cohomology theories and homology theories. This is how they should interact with each other. Okay, so this is something which is a statement which I'm not going to prove, but it follows from the classical result on coherent sheets. How the pullback and push forward, higher direct ranges, you take the pullback and push forward in the derived categories, how they behave with each other. Okay, so here, so let me write what I missed basically. I apologize for that. Here, we used the fact that k naught of x on gi of x or y. Yeah. So basically what we are saying that k naught of x, if I multiply with gi of x, I should get back to gi of x. Yeah. So let me try to give this on the generators. So here we have projective module P. Here I am giving you some class. So this is some x basically. I want to say what this is. Okay. So given a P, I have a map from m of x to m of x, which is a tensor product map. So any m, I will take any OX module and I tensor it with P, I will get an OX module. And because P is locally free, this map is actually exact. This is the exact map, exact functor, which comes out as a product. And we write induced map, say let us P tilde, with an induced map on this QIK. Sorry, yeah, so m of x to itself. Yeah, and then I will just put it here. This P tilde of x. So because this is a G theory of J of x, and this is also J of x. Right? Is it okay? So what I'm saying is that given any projective module, I have an exact functor from mx to mx. In particular, I have a map between G theories. So which means every projective module x on GI, and then one has to prove using some additive theorems in exact categories that it actually factors to this G naught of X. G naught of X, X on, sorry, it factors to K naught of X, and in particular K naught of X, X on each of GIs, and this projection formula is with respect to direction. Okay. Should I explain it more a bit? It got a bit tricky, I understand. Should I spend more time on this projection formula?
No, I think it's okay.
Is it okay, right? So point here is that there is a K naught of action on GIs that you should remember, and the projection formula looks like this. And then you have to prove it. That's up to you guys. That follows from classical algebra geometry. Okay. So now the next thing which we basically learn in algebra geometry again is this base change formula, and let's see what that is. So what is the base change? So I have such as one is square like this, Cartesian square. Then I want to define a map from G theory of X to G theory of Y prime. So there are two ways to go from G theory of X, from G theory of X to G theory of Y prime. What are those two things? Those two ways. I push forward from F with respect to F and pull back along G, or I pull back along G prime first and then push forward along F prime. Right? There are two ways to go from G theory of X to G theory of Y prime. Suppose there is, like I have to put some conditions on F and G such that this exists. Let us put those conditions. So I want F to have push forward, right, on G theory. So what I should write here, that F is a proper morphism, right? We just saw that for any proper morphism, there's a push forward on G theory. This is good. But then I want to pull back along G. So what should I write here? G should be G is of finite Tor dimension. Or you can assume flat also. Finite Tor dimension. Yeah, and then I can pull back along G. And the point here is that because the Cartesian product, if F is proper morphism, F prime will be a proper morphism. And if G is finite Tor dimension, then G prime is also finite Tor dimension. So I can pull back along G prime and push forward along F prime. The content of this base change formula is usually that these two ways actually agree under some conditions. The condition is when F, Y prime and X are Tor independent. Over Y. Yeah. So this will hold if my G is flat, because it cannot have Tor with anything in particular with X. But if I'm just demanding it to be of finite Tor dimension, I should demand that Y prime and X should not see each other if we are talking about torsion, these Tor groups. So what does this mean? Let me just spell it out. So for every X in X and Y prime in Y prime such that your F of X is actually equal to G of Y prime equal to Y, we have Tor I of OYY O X comma X O Y prime 0 for every I. So locally, like this will make sense locally, and this should happen for the each Tor. Okay, so if I take a point from one fiber of Y, like 2 points from fibers of Y, X and Y prime, this local ring should not have any torsion with respect to each other over this ring. Over. Okay. So this additional condition, because I'm not writing the proof, there's not much point of telling you this condition, but I just wanted to do that. But the point is that under this additional condition, we have this base change. And again, the formula comes from the classical formula in the derived category. When you take R and G, this formula holds. And then you see that the definition which we gave on those things where the R of F rho star is just F rho star. Okay. So it just follows from the classical thing, going to the categories, following the proof what we gave for this pullback and push forward. The existence of push forward and pull back. Is it okay? Good. Okay. So these are the kind of conditions which, when you're working with any invariant in some sense of schemes, any groups, at least you given any scheme you are shared with a group or a topological space, you can ask these kind of questions. When does Bliss change formula holds, or when projection formula holds, or if this kind of pull this becomes a functor or not. These are the obvious questions what we should ask. What we should ask. Okay. So obviously, if I'm telling you two theories and I'm calling one as homology and another as homology theory, at least there should be some duality. Okay. Yeah. So let X be a scheme. Okay. Then recall that we have these two exact categories, P of X sitting inside M of X, and this inclusion is exact. It's an exact functor. Right? So projective modules are obviously like locally free Wax modules are obviously coherent Wax modules because we can find a triangle locally free Wax modules. In Z functor input. We have group morphisms. This is an actual group morphism from K groups of X to G groups of X. I want to see when these things are same or not. And here is a theorem, which again I'm not going to prove perfectly. The above natural map. From KIX to GI of X is an isomorphism. Any guesses what condition I should put on X? When X is regular. Yeah, so duality usually holds for, if you are familiar with algebraic geometry, it usually holds for smooth states or something. And because we are not working with quasi projective, we can say that this regularity is a good condition for states. And it actually holds. And the proof, again, the ghost counts is a solution for it. Using the fact that regular schemes finite homological vector. Okay. So basically it says that because it has a finite chronological dimension. Every cox model can be resolved by a finite complex of locally free sheaves, and using that we can write this. Is it okay? So obviously, this resolution theorem, I would suggest, if you guys are really interested in this, understanding this lecture, go to the resolution theorem, see how these three theorems, like pull back, push forward, and this theorem follows from resolution theorem. What we discussed, we use it 3 times today. My plan was to go into much more details about this, but yeah, I'm going very slowly actually. Is it okay? So for regular schemes, so whatever results we talked about, this pullback and push forward on G theories, like push forward exactly, especially for regular schemes, we do get push forwards on KIs now. Right? So as a corollary, this is the kind of power of duality. It gives you push forward on corollary theories. So for proper morphism, between regular schemes, we have push forward on K groups. Is it okay? So if you are working with a say algebraic geometry, in some sense, like you're working with the smooth possibility schemes only, K theory and G theory are same, and you have a lot of nice properties. Okay, so now the question, okay, is it okay? Should I continue? Yeah. Okay, so let us try to understand why do we. So most of you might have heard, like, we always study K groups, not these G groups. Okay, or like these J groups were written as K prime groups in the book, and I guess in Srinivas he calls them G groups, or yeah, different notations are there, but usually people do not discuss these G groups. So that goes back to the idea which I was saying, that the main category associated to a scheme is the category of locally free sheaves instead of category of all coherent sheaves. Even if they are subcategory, it has, I would say, it's like category of locally free sheaves have exact properties which we need to study. It does not have two extra very nice properties or something like that. So why I'm saying this, why I made such a statement is this kind of result, nil variance. Okay. Proposition, let Z inside X be a closed subscheme such that the idea of Z is nilpotent. Yeah, for example, we can take Z X reduced inside X. Yeah, so it is structure. Then we just prove that there's a push forward map because closed morphisms are proper morphisms. There's a push forward map, and the nil invariance says that this map is actually an isomorphism. Okay. So yeah. So in particular, so let me just write it and discuss a bit, and then we will go to the proof. In particular, if I take G theory of a field, it's actually the same thing as G theory of this thickened point. Yeah. So if I take a thickened point, which means a point with some kind of thickening around it, like this dual numbers kind of these dual numbers, and take their G theory. G theory is not able to differentiate between this thickened point and a point. So this is somehow, if you want to write it as schemes, this is kind of GI of 2 of 0, and this is just GI of 0, right? Vaguely speaking. 2 0 doesn't make much sense, but yeah. Okay. 0 means like you can take a affine line and you can take this point 0, the coordinate 0, the t equal to 0 coordinate. That's just a one point, which is whose structure shape is just a. Sorry. Yeah. Is it okay?
Did you meant on the right side gi of kx by x?
Yeah, but that is exactly x, right? Exactly k.
Okay.
So if you do this, let me write maybe this thing. But this is just k, right?
Right.
So this is like k is spec k is exactly the points in our algebraic geometry. But the point of algebraic geometry, one of the main ideas of algebraic geometry is that we can talk about thickened points. And we can differentiate between taking zeros of x square and zeros of x. That's the main idea of coming to these commutative rings, because in classical geometry we just see them as points only. These two x, like x squared, zeros of x squared is just a zeros of x. But here we are saying that we can understand them in a bit different way, different flavor, because we're taking the rings and spec of them. But G theory says that there is no difference basically. But what happens? So as I said, like for smooth things they are same, and every field is smooth or regular basically. Sorry, and you know that these two things are not same in general actually. K theories of thickened point is not same thing as K theory of X. It doesn't happen. So in particular, G and K theories are also very different for similar schemes or thickened points for non-reduced schemes. Okay. So this is the point why we care about K theory much more than G theory, because we want to differentiate between the Kx by x square and Kx by x. We want to differentiate between Z and X basically. Is it okay?
Yes.
Yeah. So let us go to the proof of. So this is a side. Okay, so this is just a side. Let's discuss the proof a bit. So okay, so how to prove such a thing? So in one word, if you ask me, I will just say the research and leave it to you guys. Yeah, but let us try to see what this research mean and how to apply this. Research is the statement about abelian categories. That is, so I'm writing the statement of research first. Let this be abelian subcategory. A subcategory that of abelian category be a subcategory of an abelian category A such that it's an exact, obviously, base exact, such that for every object, M of A, there exists a filtration. So in a abelian category, we can make sense of a filtration. And finite filtration, basically, there exists a finite filtration such that all these mi plus 1 over mi, they are actually objects. They come from the objects of this subcategory, this is subcategory B. Then K theory of B to K theory of X. There's a push over map because the inclusion is an exact functor and essentially. Yeah. So if there exists a filtration such that the quotients are actually in B, then the equivalent K groups of these two exact categories are actually same. Yeah.
Rahul,
Yeah.
there's only 5 minutes left.
Yeah, sure. So I will just finish with this proof. Okay. So now we have to apply the research to our case, which is like we have to show that G theory of Z and M X are same basically. So we take A to be M of X and B to be M of Z, and note that for M in M we have filtration which is M. Then I take this ideal times M, is some module of some sub coherent module of M, and I can take Iz square of M and so on and so forth. And I have assumed, say, what's that? If so, this is nilpotent, right? So some power of this Iz will be 0. So there exists stars such that Iz are going to be 0, and then I have a finite filtration of M. We have this such that. So what happens if I take the quotients? This is ideal of Z, so let me not write Z here. This I is equal to ideal of Z. So Zi over Zi plus 1 of M. What is that? I power Z, please. So this is an element of it's an element of B, right? But this is just a module over basically Z. Is it okay? Yeah, so what we are saying that given any M, I can always give this filtration so that quotients are actually supported on Z. This Z, if M is OX module, coherent OX module, then XIM over, I power IM, I power I plus M, I plus 1M is OX mod I module. OX mod I is just OZ. So this always happens. You can give the filtration, but this filtration should terminate. And that's the condition comes from the nilpotency of this IZ. So if my inclusion is this closed immersion is nilpotent, then the K theories, G theories do not differ. Yeah, better research. Is it okay? I hope the proof is clear. Nice topic.
Yes.
Any questions? Okay. So in next lecture, basically we will do localization of G theory and localization of K theory. We'll see some localization of what is the localization for G theory and its application. I will write one application. Obviously, I will not give a proof. I will just discuss about that and give an application and try to prove the application, basically. And then we'll go to the localization of K theory and see why Thomson and Troubaud required the K theory of to know K theory of Waldhausen categories to even conclude the localization of K theory. And then if time permits, we will discuss the applications of localization of K theory.
Thank you, speaker, for the wonderful talk. Let us all thank him. And if anyone has any questions, please feel free to ask now.